Hi everyone. So in the last class we talked about the discrete logistic equation. So last time in MATC58 we talked about an approximation to the logistic differential equation, and that was the logistic difference equation, which was a discrete time approximation. So that's x sub t plus 1 is equal to r x sub t times 1 minus x sub t, where r is some parameter that controls how quickly it grows initially to start. And one of the things we noticed is that this has different behavior as r changes. So for small values of r, you have a single fixed point at the equilibrium. So the thing doesn't even, the organism, whether it's rabbits introduced to a new environment or maybe coronavirus introduced to a population, if r is small enough, then it doesn't actually reproduce, and no matter how much you introduce initially, it dies out very quickly. So let's draw that out and summarize some of the facts we know. So let's start here, and let me get a line going. So this will be the r-axis. So let's see, this is r equals 0, r equal 1, 1, 2, 3, 4, r equal 2, 1, 2, 3, 4, r equal to 3, and let me actually extend this slightly more, and r equal to 4. Okay, so in this region here, when r is between 0 and 1, recall that we had 0 is the stable fixed point. And then we also showed that, and this was part of your exercises, that between 1 and 3, you actually had your fixed points changed. So here you had your r minus 1 over r stable fixed point. Oh, just a moment, something's weird with my pen. R minus 1 over r stable fixed point. And 0 became an unstable fixed point. Okay, but what we also said that between r is equal to 0 and r is equal to 4, you do have a solution that stays between 0 and 1. So what happens between 3 and 4? Well, that behavior actually gets super duper complicated and chaotic. And I'm using chaotic here in the technical sense of it, which we'll describe in a moment. So first, one of the things that we didn't do, but which you can verify, is between 3 and 1 plus the square root of 6, which is, just a moment. So 1 plus the square root of 6, I'm just going to compute that right now since I didn't actually write this down. So that's about 3.45. So that's about here. So this is 1 plus the square root of 6 equals 3.45, roughly. So what happens in this region? Well, in this region, you have a stable 2 cycle. So let me write this out here. You have a stable 2 cycle. So 0 and r minus 1 over r are unstable. And you have a stable 2 cycle. Okay, well, then what happens going a little bit further? So this analysis gets really quite complicated, but one of the things you'll notice is that between 3.45 and this is 3.56, roughly. So, let's see, 3.56. I'm actually going to give a couple more decimal points. 3.5644. So in this region here, what you have instead is you have a stable 4 cycle. And then, if we keep on going, let me use red again. 3.5688, which is about there. 3.5688. This region here, well, you might guess, there's actually a stable 8 cycle. And so this keeps on going, and you notice that range in which you get the stable 2 cycle is bigger than the range you get the stable 4 cycle, which is bigger than the range where you get a stable 8 cycle. And this doubling keeps on happening until you get to a critical point, which I'm going to call R is 3.57. So 3.570 approximately. These are all approximations here. And in this region, between 3.57 and 4, this is chaotic behavior for most values. For most values. So what does that mean? That means you have an uncountably, let me write this out, uncountably infinite number of trajectories sometimes close together and sometimes far apart. And in the next video, we'll actually we'll show a couple of these trajectories via Python plotting. Let's see. But you'll note that I should mention for the sake of completeness that this is only for most values. It turns out that for some random values, like let's say this one here, for some values, so R is equal to 3.828 approximately. Let's see, that's a little bit hard to read, and I'm covering it up. So at approximately 3.828 is an island of stability with a 3 cycle. So this discrete logistic equation actually does all sorts of weird things. So first it starts out with the 0 as the stable fixed point, and it turns out that we also have R minus 1 over R is less than 0, which is unstable. But that's negative, so it doesn't actually matter. And then between 1 and 3, you have the stable fixed points and unstable fixed points swap. And so then R minus 1 over R is your stable fixed point. But then we have this period of cycle doubling. So stable fixed point you can think of as a 1 cycle. And then between 3 and about 3.45, you have a stable 2 cycle, and the 1 cycle becomes unstable. And then you have a 4 cycle, and then an 8 cycle, and then a 16 cycle, and so on. And it keeps on going, actually, asymptotically as you get closer and closer to this critical point, which I'm going to call RC, which is about 3.57. And then you get chaotic behavior, where you have things going all over the place. And so you have tons of different periodic cycles, and depending on where you start, you can start right next to each other, and then you go super far apart. And so this is an intuitive definition of the mathematical concept of chaos. So a tiny difference in where you start out causes the trajectory to go in wildly different places. But we're interested in understanding this sort of behavior more generally. And now we can do simulations and see this play out, and we're going to do that in the next video, which is going to be more simulation-based. But let's talk a little bit about the theory of it in this video. So as I mentioned last time, a bifurcation happens when the behavior of a system changes. So like suddenly having a stable 4 cycle when you didn't have a stable 4 cycle to begin with, and losing your stable 2 cycle because it became unstable or something like that. When the behavior of a system changes as you go past a particular value of a parameter. And here our parameter is this R value. So for R less than 3, you don't have any stable 2 cycles. For R greater than 3, all of a sudden you have a stable 2 cycle. So like that moment of transition, those are the as you move along on the R axis. That is a bifurcation. More formally, we can let's define this a little bit more rigorously. So more formally, consider a function x sub t plus 1 is equal to, instead of just f of x sub t, I'm going to have this be a function of two things, your x sub t, so your trajectory, as well as this parameter r, which is going to be constant for any particular difference equation, but we're going to be interested in varying that parameter r. Then for any value of r, for any value of R, there is a set of equilibria denoted x bar of R. So note that this isn't a function in a normal sense. So x bar of R is a set, so that can include multiple things. It can include both 0 and 1, it can include etc. if they're both equilibria. So for example, this might be equal to, e.g., x bar of R is equal to, let me give myself a little bit more space. For example, x bar of R is equal to the set 0 and, what was it, R minus 1 over R. Okay, so there's some set that we can, of equilibria. And often we actually, or I shouldn't say often, sometimes, we also include M cycles. Include M cycles in the set, x bar of R. So it depends on what kind of behavior we're talking about. So we are just using this x bar of R to denote the basically the various special points. So either equilibria or the periodic solutions of our differential equation. And this is as a function of this parameter R. Sorry, not differential equation, difference equation. Though the same sort of thing can be, the same sort of stability analysis can be applied to differential equations as well, which we'll do later in this class. So now, once we have that definition, the values of R, where x bar of R changes are bifurcation values R bar, and the points R bar, x bar of x bar are the bifurcation points. Bifurcation points. Okay, and so what happens is x bar of R, it turns out that this changes when an equilibrium or M cycle changes behavior. Or M cycle changes behavior. So strictly speaking, you have to be a little careful. So I've denoted these as, I've called these sets, but they're not really sets because we're associating we take a look at all sets of equilibria and we also look at their stability for that. And so when do these things change behavior? Well, by the first derivative test, they change behavior when the derivative has absolute value 1. So that is when the derivative of f or f to the m, if you're looking at M cycles, has absolute value 1. Because you recall, when you have absolute value 1, you have to go to the further derivative test. But we're not going to worry so much about that, and just say that below the absolute, less than the absolute value 1, you have stable. Above absolute value 1, you have unstable. And this is true for both equilibria and M cycles. And so the set of equilibria changes whenever one of the derivatives at one of our bifurcation points has absolute value 1. And so we can plot this visually, which is the usual way this is depicted, is something called a bifurcation diagram. So bifurcation diagram plots x bar of R as a function of R. So recall that this is a set, and so you have some value of R on the horizontal axis, and then you can, on the vertical axis, you can plot each of the different equilibria points. And we can actually, in our bifurcation diagrams, we usually also specify the additional information of if they're stable or unstable. And sometimes we might also specify the additional information if we're talking about cycles or just equilibria. So we're going to use using a solid line for stable equilibria line, oh, I already wrote line, for stable equilibria, or M cycles, and a dashed line for unstable equilibria, or M cycles. Let's give an example of this, because this is a little bit weird of a definition to use, and I don't think it's so obvious without drawing a picture. So I'm going to use a very simple example. X sub t plus 1 is equal to r plus x sub t plus x sub t squared, for minus 1 is less than r is less than 1. Okay, so what are the equilibria? Well, that's easy enough, right? So then we know that x bar is equal to r plus x bar squared. And I am abusing notation a little bit to refer to both the set of equilibria as well as each individual equilibrium. But this implies that minus r is equal to x bar squared. Minus r is equal to x bar squared, which implies that x bar is equal to plus or minus the square root of minus r, if r is less than 0. So if r is greater than 0, then you don't have any real equilibria because they're imaginary. Let me make sure this is clear. That's minus r. And we'll note that f of x is equal to r plus x squared. So f prime of x is equal to 1 plus 2x. Okay, and we know by using the first derivative test that we can figure out when things are stable or unstable. So let's see, f prime of the square root of minus r is equal to 1 plus the square root of 2 times the square root of minus r, which is which is greater than 1 for any r that's less than 0. For r less than 0, so unstable. And imaginary if r greater than 1, greater than 0. So we don't need to plot that. Let's see, let me put complex. So it is actually imaginary in this particular case. So that's unstable. And then we also have that f prime of minus the square root of minus r is equal to 1 minus 2 times the square root of minus r, which is a little bit more complicated. So let's take the absolute value of that. So the absolute value of x prime of minus the square root of minus r is, this is less than 1 if r is greater than minus 1, so that's stable. And this is f prime of minus the square root of minus r is greater than 1 if r is less than minus 1, so unstable. But luckily, we're only looking at the range from minus 1 to 1, and so we don't have to worry about less than minus 1. So we're going to care about the transition at the point x is equal to, so we're going to care about the transition at the point r is equal to 0. And so we are including this for completeness. There's a different transition that happens when r is equal to minus 1, as you can see from this change in stability here. So now let's plot this out. So let's give ourselves a couple axes. And let's do, oh, no. Okay. So what does this look like? We have, let me use that. So this here is the r-axis, and this here, we put x bars on the vertical axis. And so we know that there's nothing to the right of the vertical axis because that there r is positive, and we only have equilibria if r is less than 0. So therefore, we have two different equilibria. We have the square root of minus r, and we have the minus the square root of minus r. And so it turns out that this is just a sideways parabola. So we have let's do the positive one first. So that's unstable, right? And so this goes something like, let's say this is, oh, that was the wrong button. Say this is 1 and this is -1. And we're only going to care about it in this range. So, drew it too far. And it's unstable below the negative not eigenvalue. The negative equilibrium is unstable. And so this here is a, wait a moment, did I get that backwards? Yes, I got that backwards. So, because we're using dashed lines, so I said it correctly, but we're using dashed lines for unstable. So this one here is unstable. And this one here is stable. Okay, so this is a bifurcation diagram, and then something else would happen here. So that becomes unstable, and then you might have other cycles appearing, but we're not going to discuss that since we're focused at this point. So this is the bifurcation point. Because that's because to the left of the bifurcation point, you have these two equilibria. One of them is stable, and one of them is unstable, and the other unstable. And then past that point, you no longer have either of them. They both disappear. And it turns out that we can actually classify most of the basic bifurcation types. And so recall that the basic bifurcations are the ones where f, the first derivative, is plus or minus 1. So let's classify those. Classification of bifurcations, where f prime of x bar of r bar is equal to plus or minus 1. The first one we'll see is exactly what we just saw. So this is a saddle node, or it's sometimes called a tangent. Or it's sometimes also called a blue sky bifurcation. And just as a note, in this particular case, f prime of x bar of r bar is equal to 1. As you can see from in the previous example. So this is a blue sky bifurcation because if you go from the right to the left, sorry, everything's mirrored for me. As you go from the right to the left, you'll see that you don't have any equilibria, and then all of a sudden you have two equilibria. They just pop out of nowhere. And so these all have this characteristic shape. Though you can go from the right to the left or left to the right, it doesn't really make a difference. So these are things that look like that. So you have two different equilibria. One of them stable and the other is unstable. You can swap the order of them, but so a saddle node is you have a pair of equilibria, one unstable and one stable. Equilibria. One stable, one unstable. And they either disappear or appear together, depending on which way you're looking. Okay, and of course our example is just the one we gave above. So example, x sub t plus 1 is equal to r plus x sub t plus x sub t squared at the point r equals 0 as shown above. And there are a couple other types of bifurcations, and we'll give examples of some of them, and you'll be covering some of the other ones in your homework. So let me give a pitchfork bifurcation. So this is going to be one of the homework assignment problems. But let me give you what it looks like first. So again, let's draw our bifurcation diagram. And the reason it's called a pitchfork is because you have one equilibrium, let's call it a stable one, and then it turns into two other stable equilibria and an unstable equilibrium. Or you can have the opposite. So you can have an unstable equilibrium that turns into two unstable equilibria and a stable equilibrium. So it splits off in this characteristic pattern. And the two different patterns have different names. So this one is supercritical, and this one is subcritical. And the supercritical one's actually really interesting because it leads to a biological phenomenon called hysteresis, where the stable state of your system depends on the history. Because if you look over here, we have two different stable equilibria. And so if your system, depending on where your system was, and so even as you sweep, even if you change the R value, where your system actually is may depend in practice on the history of it. And we'll talk a little bit more about that when we get to some actual examples of biological models. For now, you can just think of it mathematically as a stable equilibrium becomes two stable equilibria separated by an unstable equilibrium. So a stable fixed point becomes two stable fixed points. Two stable fixed points separated by an unstable point. And the subcritical one is obviously just the opposite. So an unstable fixed point becomes two unstable fixed points, separated by a stable fixed point. Okay, and I'm not going to give an example of that right now, but that, like I said, that is something we're going to cover in the breakout session problems. Okay, and I should mention for completeness that for this type of bifurcation, you still have f prime of x bar of r bar is equal to 1. So it's equal to positive 1. The next one, which we've seen before, we saw this in our last set of lecture notes. This is as well as in our example above. So this is a transcritical bifurcation. So what does it look like? Let's say we have our diagram. So this is the r-axis, this is the x-bar axis. And let's suppose we have an unstable equilibrium and a stable equilibrium, and they meet, and then they change their behavior. So then this equilibrium becomes, let me make sure the show this continues. That continues, and this one becomes unstable. So you start out with two fixed points of opposite stability, and they exchange stability. So they swap stability as the bifurcation point is passed. And so we saw an example of this earlier in the discrete logistic equation. So x sub t plus 1 is equal to r x sub t times 1 minus x sub t at r is equal to 1. So above, when 0 is less than r is less than 1, 0 is stable, and x bar is equal to r minus 1 over r is negative. So we don't normally plot it when we're looking at we don't normally plot it when we're looking at biological systems, but if you were to, because you can just analyze these difference equations as mathematical objects, but also unstable. However, when we go to r greater than 1 less than 3, 0 is unstable, and x bar equal to r minus 1 over r is stable. So that's an example of a transcritical bifurcation. And we'll give one final type. Oh, I should mention for completeness that again here, f prime of x bar of r bar is equal to 1. Okay, and we have a final fourth type of, that's the wrong color. We have a final fourth type of basic bifurcation. This is one that actually only exists for difference equations and doesn't exist for differential equations. But this is called the period doubling or flip bifurcation. And in this particular case, f prime of x bar of r bar is equal to -1, which is different from the other three types of bifurcations we're talking about. And this has a very characteristic look. And it's a little bit more complicated because we're going to have our bifurcation diagram show both fixed points and also 2 cycles. So let me draw this out. And part of the reason this is specific to difference equations is because you don't have the concept of a 2 cycle is something specific to the sort of discrete time case. And so, okay, so you start out with, say, a fixed point. It passes the bifurcation, and then it becomes unstable. Or it starts out stable. Or sorry, it becomes, it starts out unstable and then becomes stable. Okay, but the cool thing about these period doubling bifurcations is that when that fixed point passes, I'm going to use a different color here. You then end up with a 2 cycle that's stable, or a 2 cycle that's unstable. So instead of the fixed point becoming two different fixed points, the fixed point becomes a 2 cycle that's separated by an unstable equilibrium. And again, this is very similar in some sense to the pitchfork bifurcation, but it's different because instead of going from equilibria to 3 equilibria, it's going from a fixed point to a swapped stability fixed point and to a 2 cycle. So this is supercritical, and this is subcritical. So we use the same terminology. And you note that we are discussing this only for the case of going from a fixed point to a 2 cycle, but the same sort of bifurcation happens when f double prime of x bar, or bar, etc. is equal to -1, going from a 2 cycle to a 4 cycle, or a 4 cycle to an 8 cycle, and so on. And so this is why we call it a period doubling of bifurcation. So a stable fixed point becomes unstable as a stable 2 cycle appears. Or an unstable fixed point becomes a stable fixed point as an unstable 2 cycle appears. And so we saw this earlier, but let me, I should mention and write down my aside that the first 3 bifurcations, those 3 types also appear in differential equations. But the period doubling bifurcation is unique to difference equations, because you need to have a discrete period for this to make sense the way we've defined it. So there are a couple different examples. I'm going to start with one of the easier ones, one of the ones we've already covered. So in this example, x sub t plus 1 is equal to r x sub t times 1 minus x sub t at r is equal to 3. Alternately, so we already covered that one, so that's just the discrete logistic equation. But if you look at, I mentioned that there was weird behavior for the other example we talked about earlier, t squared, when r is equal to -1. So remember I said that weird stuff happened at -1, but we were only looking at when r is equal to 0. When r is equal to -1, weird stuff also happens again. So I'm not going to do all the computations here, because we've already done some of them and they're a bit tedious. So the equilibria, the equilibria are, I'm going to use imaginary numbers just because saying the square root of a minus number is a bit weird. So minus I square root of r, or I square root of r. And so when r is negative, this is real. So again, we need to have r negative for any of this to make sense. And there's also a 2 cycle, which is minus I times the square root of r plus 1 minus 1, or I times the square root of r plus 1 minus 1. So you can solve this by just solving for f of x is equal to f of x, using something like Wolfram Alpha or MATLAB or any other computer algebra system. So that's the 2-cycle, and so sometimes you'll note that when r plus 1 is negative, well then this is real. When r plus 1 is positive, well this is complex, and so we don't care about it for the purposes of our analysis. Let's see. So f of x is equal to r plus x squared. F prime of x is equal to 1 plus 2x, as before. So we have that f prime of minus I times the square root of r is greater than 1 if r is less than minus 1. We already did that. So we just don't, that's an unstable equilibrium above the, that's, where was I? That is this unstable equilibrium. So we're not going to worry about that so much right now. Instead, we're going to worry about this stable equilibrium right now. We're going to focus on that one. So note that when r is less than minus 1, the 2-cycle is real. Also, we can look at the stability of this 2-cycle. So you take the stability, so that's f prime of minus I times the square root of r plus 1 minus 1 times f prime of I times r square root of r plus 1 minus 1. And this is equal to the absolute value of 1 plus 2 times minus I times the square root of r plus 1 minus 1 times 1 plus 2 times the square root of I times the square root of r plus 1 minus 1. If we expand that out, that's equal to the absolute value of minus 1 minus 2i times the square root of r plus 1 times minus 1 plus 2i times the square root of r plus 1, which is equal to 1 plus 4r plus 1, which is equal to the absolute value of 5 plus 4r. And it turns out that this is less than 1 when r is greater than minus 3 halves, and less than minus 1, and greater than 1 when r is less than minus 3 halves. So thus, when r is less than minus 1, so immediately after it goes past minus 1, you end up with a stable 2-cycle. So then a stable 2-cycle, a stable fixed point turns unstable, and a stable 2-cycle appears. Appears at r is equal to minus 1. Okay, so that was a really quick overview of a classification of all these different bifurcation types for fixed points in difference equations. So in the next video, we'll be talking a little bit about, we'll be illustrating some of these by using computer simulation. So you get a better sense of the intuition for the actual behavior of the system, rather than just seeing the sort of theoretical bifurcation diagram view of things. So I will see you in the next video.